We'll be looking at question 17 from the October 2020 paper. This question is asking about methanol that can be made industrially by reaction of carbon monoxide with hydrogen as shown in this equation. You've got our equation here. It's in the equilibrium setting. It says predict the conditions of the pressure and temperature that would give the maximum equilibrium yield. So we are after as much yield of methanol by looking at the two factors of pressure and temperature. Before we even answer this question, let's have a look at what this equation is giving us. You see on the left-hand side, we've got 1 here and then 2 here, 3 moles of gas. On the right-hand side, there's only 1 mole of gas. We'll come back to this in a moment. You see also the forward reaction is exothermic. That means the reverse reaction must be. So we need these bits of information to help us answer. We want the equilibrium to shift to the right-hand side. And the only way it can do that is by using a high pressure. Why high pressure? As there are fewer moles of gas on the right-hand side. Le Chatelier's principle states that when a system is in dynamic equilibrium and is subjected to a change, the equilibrium will shift to oppose that change. By raising the pressure, the only way it can bring the pressure back down is by shifting to the right-hand side, which has fewer moles of gas. 3 moles of gas go on to produce 1 mole. So we've got a high pressure. Let's look at temperature. You see, for temperature, we'd actually use a low temperature. And why will we use a low temperature? As the forward reaction, by lowering the temperature, you've disturbed the equilibrium. And to oppose that change, it is going to want to bring the temperature back up. And for that, we need the exothermic reaction is favored, which is the forward reaction. So low temperature as forward is exothermic. Yep. And that's it, covers all the points there. A catalyst is used in the production of methanol. State 2 ways that the use of a catalyst helps chemical companies to make their processes more sustainable and less harmful to the environment. So making it more sustainable. For sustainable, ideally, you want to be using as much, you want to be as energy efficient as possible. And we know that a catalyst lowers the activation energy. Therefore, lower temperatures can be used. Or we could say low. And if less or a lower temperature is needed, saying my internet connection is unstable. If a lower temperature is needed, therefore less fossil fuels will be burnt. Which makes it less harmful to the environment. Moving on. It's asking here, at this temperature. We've got our entropy values. Standard entropy values are given there. You got the temperature at which this is taking place. So we're going to use that expression. Delta G is equal to delta H minus T delta S. Before we even do this, we need to work out the entropy change. And the entropy change we work out as products minus reactants. So it's going to be methanol 238 minus, there's two hydrogens, minus 2 times 131 plus 198. This gives you the entropy change. Two, and remember, this is in joules per Kelvin per mole. So we're going to have to, when we're using it in the expression above, we're going to need to convert the joules into kilojoules. So what we got here, delta H is given in the question, minus 91. So let's do delta G is equal to minus 91 minus T, which is given in the question, temperature, multiplied by minus 222 over 1000. See what this gives us. That gives you 25.55 kilojoules per mole. And you see, it's not a negative value, so it's actually a positive value. So delta G is greater than 0, which does not make this reaction feasible. So 4 marks are for 25.55, and 1 mark is for, the statement saying that it's not feasible because delta G is greater than 0. Just a reminder, entropy change is products minus reactants. At this temperature, the free energy change for the production of methanol is given. At this temperature, delta G is linked to Kp by the relationship. Oh my goodness, we have never seen this expression before. I don't remember ever teaching this in class. Do we know what R is? Yes, we do. It's the gas constant. We know what temperature is. And we do know what Kp is, but they're referring to the natural log of Kp. So they are using theory that we already know, but they're presenting it in a different way. A bit of an extension question, but let's see how this plays out. It's asking us calculate Kp for equilibrium 1 at this temperature. Give your answer to 3 sig figs. Let's have a go. Never done this kind of question like this before. Let's see. Is given. Let's write this all down again. Delta G is equal to minus RT natural log Kp. So what we will do, it's going to be minus 2.48 times 10 to the 4 equals minus RT. So this is minus 8.314 times the temperature 298 multiplied by the natural log of Kp. So let's rearrange that and work out the natural log of Kp by bringing R and T to the other side, minus. So for K, this gives us 10.009799992, and then we take the E of that, E of ln Kp. E and natural log is an inverse of each other. This will give you Kp. So on my calculator, E of the answer, and this gives us, they want it to 3 sig figs, so 22200 at the units of Kp. Kp is products over reactants. Products over reactants, which is the partial pressure of methanol over the partial pressure of carbon monoxide. Is it monoxide? Partial pressure of hydrogen, but squared. Each partial pressure now we can assume the partial pressure, if you're looking at on an industrial level, actually just have a peek at the mark scheme, and it doesn't matter which units you use. So it's 1 over pressures, partial pressure squared. So you could do ATM, atmospheric pressure, to the -2. Yep. And Kp is, they've given it in standard form, 2.22 times 10 to the minus 10 to the 4, 2.22 times 10 to the 4, and it says allow 22200. Yep. That is the end of that question, ladies and gentlemen. I will see you tomorrow.